Welcome to Techno Sapiens.
Okay, I want you to pause for just a second and think about your morning commute, or, maybe the last time you took a walk around your neighborhood. Now, in your mind's eye, I want you to look up. Spanning right across our skies, towering over our highways, cutting through the landscape, there's this massive, sprawling infrastructure that we literally see every single day, yet we almost entirely take it for granted. Yep, I'm talking about power lines, those towering metal giants holding up massive wires. So in today's explainer, we're going to completely demystify them. We're breaking down the sheer physics and the rigorous engineering that keeps our modern world powered and, crucially, keeps us safe. So why exactly are these power lines built so incredibly high up? I mean, why not just string them, say, a few meters above our heads and save an absolute ton on steel and engineering costs? Well, as it turns out, the answer isn't just one simple thing. It's actually this fascinating intersection of thermodynamics, the fundamental properties of electricity, and hardcore structural engineering. And by the time we wrap up this explainer, you'll see that every single inch of vertical height on those towers serves a vital, highly calculated purpose. Let's start with the most obvious reason first. Section 1, clearing obstacles and vehicles. Right off the bat, engineers have to establish a foundational clearance baseline simply to account for human infrastructure. Our roadways are shared with towering commercial trucks, construction equipment, cranes, and positioning these lines too low, well, that would create a constant, catastrophic hazard. But it's actually not just about massive trucks. Keeping this baseline height protects the power system itself from its own environment. Think about it. A single stray tree branch just brushing against a live transmission line can cause an instantaneous short circuit, and that can damage critical equipment, throw dangerous sparks, or literally trigger a massive power outage for thousands of people. So that baseline height provides a completely necessary physical buffer against the unpredictable world right below it. Section 2, the science of electrical arcing. To truly wrap our heads around electrical clearance, we have to look past those physical obstacles and confront a completely invisible danger. See, electricity doesn't always need direct physical contact to become deadly. We're not talking about a little trickle of energy here. These transmission lines are carrying hundreds of thousands of volts. Under that immense electrical pressure, the air itself, which, normally acts as a really reliable insulator, can undergo what physicists call dielectric breakdown. The sheer voltage literally strips electrons right off the surrounding air molecules. It ionizes the gas and turns it into a highly conductive plasma channel. Basically, the electricity jumps or arcs right through the air. So, maintaining a massive safety distance isn't just some precaution, it is a strict mathematical requirement dictated by the pure physics of dielectric breakdown. Section 3, heat, weather, and wire sag. Now, power lines are absolutely not static objects. They are dynamic metal conductors that are constantly reacting to thermodynamics. As the temperature rises, these metals undergo thermal expansion. And hey, this isn't just caused by a hot summer day. As immense electrical current pushes through the natural resistance of the metal wire, it generates its own significant internal heat, a process known as Joule heating. So between the ambient weather outside and that internal Joule heating, the metal physically expands, and those wires sag lower toward the earth. Because of this, engineers literally have to calculate the material's exact coefficient of thermal expansion. They have to ensure that even at absolute maximum operating temperatures, the lowest point of that wire sag still maintains a safe distance to prevent initiating that dielectric breakdown we just talked about. Section 4. Why not go underground? It's a highly practical question, right? If overhead lines are so vulnerable to physical hazards, thermal expansion, and jumping electricity, burying them just seems like the obvious solution, doesn't it? Well, the physics makes this incredibly complex. Underground cables require intense, heavy physical insulation to prevent the exact dielectric breakdown we've been discussing, and that makes them astronomically expensive to manufacture, install, and repair. On top of that, burying them traps all that internal Joule heat, which makes cooling a massive engineering hurdle. With overhead lines, the ambient air acts as both a completely free insulator and a highly efficient free cooling system. That right there is exactly why towering overhead lines remain the undeniable standard for moving power across vast distances. Section 5, calculating safe electrical clearance. So this brings us to the ultimate synthesis of all these hazards. Engineers don't just guess a height and hope for the best. They use complex calculus to balance all these variables simultaneously. They weigh the dielectric breakdown threshold of the specific voltage against the maximum thermal sag expected from peak Joule heating.
Then they layer on worst-case weather scenarios. They're calculating the added physical weight of winter ice accumulation and the extreme sway caused by high winds. Finally, they factor in that foundational clearance needed for human infrastructure. It is an intricate mathematical balancing act that dictates exactly how tall those structures must be before a single ounce of steel is ever even fabricated.
As the quote goes, they are high above the ground for a reason: to protect people, to allow vehicles to pass, to prevent dangerous contact. These towering structures aren't just there to dominate the horizon or look imposing. They are meticulously designed silent protectors. Their grand height is precisely what keeps immense electrical power flowing safely across our grid without harming the dynamic world moving directly beneath it.
So I have to ask, will you ever look at a power line the exact same way again? The next time you see those giant transmission lines stretching across the landscape, I really hope you don't just see metal and wire. I hope you see the thermodynamics, the thermal expansion, and the invisible boundaries of dielectric breakdown holding it all safely together. Keep looking up, keep asking questions, and keep focused on learning. Thanks for hanging out with me for this explainer, and I will catch you in the next one.